So currently, AI systems are in many ways very stupid. That model does not work if you want the system to understand the physical world. And what we're missing is...
Yann LeCun is one of the fathers of artificial intelligence, and today he announced the closing of the largest seed funding round in Europe's history.
So one of the things that my colleagues and I have been working on is designing a new type of AI systems.
His new startup, AMI, has raised over 1 billion euros in funding, opening a new path for the development of artificial intelligence.
That would be capable of understanding the physical world, have persistent memory, be able to reason and plan. Those systems will have emotions.
You said machine learning sucks.
The reason why we can't find a good definition of consciousness is because we're not asking the right question.
Believing that LLMs are a dead end, he wants to create a new digital world model, giving robots the ability to understand multiple dimensions of reality.
Musk said that Tesla would reach 5-level autonomy within the next 5 years.
He's been saying this for the last 8 years.
What made your work with Geoffrey Hinton, your deep learning work, such a game changer?
So you're probably referring to a paper that Jeff Hinton, Yosha Benjo, and I published in Nature in 2015. And this was not new work. It was basically a bit of a manifesto, if you want, or a review paper to tell the wide community of science and researchers there is this new set of techniques that work really well. Here is a list of things where it works well. Here is where the future is going. And so it sort of marked the sort of public beginning, if you want, popularization of deep learning. But there was no new result in that paper, really. The new results, and most of the other citations, go back to the work that I did in the 1980s and 90s.
Do you remember the moment when that popularity was beginning?
There were two waves, really. It happened twice. So the first one was in the late 80s, when we started to have really good results using multi-layer neural networks. So we now call this deep learning for tasks like image recognition. At the time, we could not recognize complex images. It was more like simple images like handwritten characters and things like this. But this was working really well. And I was really excited at the time when we started getting those results, because I thought this may completely change the way we do pattern recognition and eventually computer vision and perhaps AI more generally. And so there was a wave of excitement between the late 80s and mid 90s. And then the interest kind of disappeared in the mid 90s. It's because the techniques that we had developed required a lot of data for training. And we could only get good data. This was before the internet, so we could only get good data for a few applications, things like handwriting recognition, character recognition, and speech recognition, but that was about it. And it required computers that were at the time really expensive, and it was a big investment. So interest in this kind of disappeared in the mid-90s. And then interest sort of went up again slowly in the 2000s, the late 2000s, and it totally exploded around 2013. So in 2013 is really the key year where the research world realized that deep learning really worked well and could be applicable to a lot of different things. And it's been kind of growing really, really quickly since then. And 2015 was another turning point.
We push AI to match the human capabilities today. Will we pick up the human flow?
No. I think, so currently AI systems are in many ways very stupid. We are fooled into thinking they are smart because they can manipulate language very well. But they don't understand the physical world. They don't really have any persistent memory of the type that we have. They can't really reason, and they can't plan. And those are essential characteristics of intelligent behavior. So one of the things that my colleagues and I have been working on at FAIR and at NYU actually is designing a new type of AI system, still based on deep learning, that would be capable of understanding the physical world, have persistent memory, be able to reason and plan. And in my opinion, once we succeed in building those systems around this blueprint, those systems will have emotions. So they'll have emotions like maybe fear or excitement or elation, because those are anticipations of outcome. Those systems will basically work by having a goal that we set them to fulfill. We'll give them goals to accomplish. And then they will try to figure out what kind of actions can I take so that I fulfill that goal. If they can predict in advance that this goal will be fulfilled, it will kind of make them happy, if you want, okay? Or if they predict that they can't, it will not make them happy. So to some extent, they will have emotions because they'll be able to anticipate the outcome of a sequence of actions they might take. But we will not hardwire into them anything like anger or or jealousy or anything like that, because there is no reason. But consciousness is something else. We don't know what it is really. There's no definition. There's no definition of it. There's no kind of measurable thing really that can tell us whether something is consciousness or not. Like even if we observe like animals, so we would probably all agree that apes and monkeys are conscious, and maybe elephants and maybe animals of that type.
That's what Roger Penrose said in our interview.
But like is a dog conscious? Is a rat conscious?
Where is the barrier?
Conscious? Where is the barrier? Like because we don't have a good definition for it, we really can't tell.
You said machine learning sucks. Was something changed?
That's what we're working on.
When you look at AI development today.
Well, we're working towards new ways of building machine learning systems so that they can learn as efficiently as humans and animals. Because currently it's not the case, okay? And I can tell you a little bit of the history of how machine learning has progressed over the last couple decades. So there's really three paradigms of machine learning. One is called supervised learning, which is the most classical one. And so the way you train a supervised learning system is that, let's say a system that is meant to recognize images. You show it a picture, let's say of a table, and you tell it this is a table. Okay, so it's supervised because you tell it what the correct answer is. The system computes its output, and if it says something else than table, then it's going to adjust its parameters, its internal structure, so that the output it produces gets closer to the output you want. Okay, and if you keep doing this with lots of examples of tables and chairs and cars and cats and dogs, eventually the system will find a way to recognize every image you trained it on, but also images it's never seen that are similar to the one you trained it on. Okay, this is called a generalization ability. There's another paradigm which people thought was closer to the way animals and humans learn, called reinforcement learning. So in reinforcement learning, you don't tell the system what the correct answer is. You only tell it whether the answer it produced was good or bad. And to some extent, that can explain some type of human and animal learning. You try to ride a bike, and you don't know how to ride the bike, and after a while you fall, so you did something bad, and so you change your strategy a little bit, right? And eventually you learn how to ride a bike. Now it turns out reinforcement learning is extremely inefficient. It works really well if you want to train a system to play chess or play Go or poker or something like that, because you can have the system play millions and millions of games against itself and basically fine-tune itself. But it doesn't really work in the real world. If you want to train a car to drive itself, you're not going to do it with reinforcement learning. It's going to crash thousands of times. If you want to train a robot to learn how to grab things, reinforcement learning can be part of the solution, but it's not the complete answer. It's not sufficient. So there is a third form of learning called self-supervised learning. And this is what has enabled the recent progress in natural language understanding and chatbots. And in self-supervised learning, you don't train the system to accomplish any particular task. You just train it to basically capture the structure of its input. So the way this is used for text, for example, for language, is that you take a piece of text you corrupt it in some way by, for example, removing some words. And then you train a big neural net to predict the words that are missing. Okay, a special case of this is that you take a piece of text, and the last word in that text is not visible. And so you train the system to predict the last word in that text. And this is the way large language models are trained on. Every chatbot is trained this way. Technically, it's a little different, but that's the basic principle. Okay, so that's called self-supervised learning. You don't train the system for a task, you just train it to learn the internal dependency of the input. And the success of this has been astonishing. It works amazingly well. You get systems in the end that seem to really understand language and be able to understand questions if you fine-tune them to answer questions properly using supervised learning or reinforcement learning. So this is what everybody has been working on in the industry, right? But that model does not work if you want a system to understand the physical world.
Something is missing.
Yes, it's just that the physical world is much more difficult to understand than language. We think of language as the epitome of intelligence because only humans can manipulate language. But it turns out language is simple. And it's simple because it's discrete. It's a sequence of discrete symbols. There's only a finite number of possible words in a dictionary. And so you can never train a system to exactly predict what word is going to come next, but you can train it to produce something like a score for every word in a dictionary or a probability for every word in a dictionary to appear at that location. And so you can handle the uncertainty in the prediction that way. But you cannot train a system to predict what's going to happen in a video. People have tried to do this. I've tried to do this for 20 years. And a lot of people have had this idea that if you could train a system to predict what's going to happen in a video, then that system will implicitly understand the underlying structure of the world, intuitive physics, everything that any animal and any of us as babies
All
learn.
physical rights.
Yeah, physical intuition. If you know that if I take an object and I let it go, it's going to fall. You've learned that gravity basically attracts every object towards the ground. Human babies learn this by the age of 9 months, roughly. It takes about 9 months to learn.
Maybe natural limitation of AI development today, it's our knowledge about the reality. We cannot replace more that we know.
Yeah, but it's a simpler problem because your cat or your dog can learn about gravity in just a few months, right? And the cats are really, really good at this, right? I mean, they can plan complex actions and climb on all kinds of stuff and jump. So obviously they have a very good intuitive understanding of what we call intuitive physics. And we don't know how to reproduce this with computers yet. And the reason is, it's another example of what AI researchers have called the Moravec paradox. So Hans Moravec was a roboticist, and he made that point, like, how come we can have computers play chess and solve mathematical puzzles and things like this, but we can't get them to do physical things like manipulate objects that animals can do, or jump, or things like that. So it's another example of this paradox, that the space of discrete objects and symbols is easily manipulated by computers, but the real world is just too complicated yet. And the techniques that work in one case don't work in the other case. A good way to kind of visualize this, if you want, is that the amount of information that gets to us through our senses, let's say vision or touch, is absolutely enormous compared to the amount of information we can get through language. Okay, and this may explain why we have LLMs, chatbots. They can pass the bar exam, or they can solve mathematical problems, or write text that sound good. We still don't have domestic robots. We still don't have robots that can accomplish tasks that a cat or a dog can accomplish. We still don't have completely autonomous level 5 self-driving cars, and we certainly don't have self-driving cars that can train themselves to drive in about 20 hours of practice like any 17-year-old. So clearly we're missing something big, right? And what we're missing is, how to train a system to understand complex sensory input like vision.
And this is necessary if we want to learn machines as professionally as humans and animals?
Yeah, if we want machines that have intelligence that is similar to that of animals and humans, that have common sense, perhaps at some point have consciousness and everything, but like are capable of really sort of learning really complex structure of complex worlds, we need to crack that problem. So we've been working on. Let me give you a very simple calculation.
Yeah.
A big language model today, a typical large language model, is trained with something on the order of 20 trillion tokens, right? 20,000 billion tokens. A token is like a word, more or less. A token typically is represented on 3 bytes. Okay, so 20 or 30 trillion tokens, each on 3 bytes. That's about 10 to the 14 bytes, a 1 with 14 zeros behind it. This is the totality of all the text available publicly on the internet. It would take any of us several 100,000 years to read through that material. Okay, so it's an enormous amount of information. But then you compare this with the amount of information that gets to our brain through the visual system in the first 4 years of life, and it's about the same amount. In 4 years, a young child has been awake a total of about 16,000 hours. The amount of information getting to the brain through the optic nerve is about 2 megabytes per second. Do the calculation, and that's about 10 to the 14 bytes. It's about the same. In 4 years, a young child has seen as much information or data as the biggest LLMs. And what that tells you is that we're never going to get to human level AI by just training on text. We're going to have to get systems to understand the real world. And that understanding the real world is really hard.
On your LinkedIn and Facebook, you are linking AI and entropy. What's the link?
It's been a bit of an obsession of mine. Like, there's a big question which is at the root of a lot of problems in computer science, in physics, information theory, in a lot of different fields, which is the question of how you quantify information. Okay, how much information resides in a message? And the point I've made multiple times is that the amount of information in a message is not an absolute quantity, because it depends on the person interpreting this message. The amount of information you can extract from sensors, from a message language that someone tells you or whatever, depends on how you can interpret that. And so the idea that you can measure information in absolute term is probably false. Every measure of information is relative to a particular way of interpreting that information. So that's kind of the point I was making. And this has very far-ranging consequences, because if there is no absolute way of measuring information, that means there's a lot of notions in physics that don't really have, kind of objective definitions, like entropy. So entropy is a measure of our ignorance of the state of a physical system. And of course, that depends on how much you know about the system. And so I've been sort of obsessed with this idea of trying to find good ways of defining entropy, complexity, or information content that is relative.
Don't you think that our global database to train AI models is over?
So we're not even close. No, there's a huge amount of textual knowledge that has not been digitized. Maybe in a lot of the developed world, a lot of it has been digitized, but most of it is not public. There's a lot of medical data, for example, that is not public. And then there is a lot of cultural data, historical data, in a lot of regions in the world that is not accessible in digital form. Or if it is in digital form, it's in the form of scanned documents, so it's not, text or anything. So so it's not true. I think there's still a lot of data out there that
and that questions about the nature of the reality, because, for example, we have no idea how matter is transformed into consciousness in the human brain, so we have no data about it. But maybe in the future we will do this.
Well, so I don't think we should be obsessed by the question of consciousness. I think it's
But the world is obsessed, I think.
The world is, I mean, some parts of the world are obsessed by it. Frankly, I think it's a bit of an epiphenomenon, and I think it's probably the reason why we can't find a good definition of consciousness is because we're not asking the right question. Let me give you an example. In the 18th century, people discovered, or the 17th century, they discovered that the image on the retina,
Iris, okay.
Light comes through the iris, and you have a lens, and the image on the retina forms upside down, right? And so the people at the time were completely puzzled. How is it that we see the world right side up, even though the image is formed upside down in our retina? Okay, that was a puzzle for them. And now we realize that question makes no sense. I mean, it's just that, the way you think about, how your brain interprets images, it's irrelevant, in what direction the image forms on your retina. So I think consciousness is a bit like this. It's something that, we can't define, we think exists, but we can't put our finger on it.
And what make us individuals. So maybe
that's different.
Why.
That's different. No, obviously, I mean, there's a lot of things that, make us all different from each other. We have a different experience. So we learn different things, right? We grow up in different environments, but also our brains are wired slightly differently. All of us are slightly different. And that's a necessity for evolution to make sure that every individual human is different, because we are a social animal. So there is a big advantage when different people in the same tribe are slightly different, because that means they can combine their expertise. If every one of us was identical, then there would not be strength in number. Okay, but because we're different, we're stronger because we're diverse. So that's a result of evolution, and that can be done by slightly different wiring of the brain, slightly different tuning of the different neurotransmitters and hormones and whatever that makes us different.
What's about the free reasoning, abstractional thinking models? Can we expect something like this from your laboratory?
So the question of elaborating abstract representations from observation is key to deep learning. Deep learning is all about learning representations. In fact, one of the main conferences on deep learning is called International Conference on Learning Representations, which I co-created with Yoshua Benjo. So this tells you how central this question of learning abstract representations is to AI generally, and to deep learning in particular. Now, if you want a system to be able to reason, you need another set of characteristics. Basically the act of reasoning or planning, classically in AI, not just in machine learning based AI, but since the 1950s, consists in having a way of searching for a solution to a problem. Okay, so for example, if I give you a list of cities and I ask you, give me the shortest circuit that goes through all those cities. Okay, you're going to think about it and say, well, I should go from cities that are nearby so that my total circuit is as close as possible. Now, there is a space of all possible circuits, which is a set of all permutations of the cities, right, in all the orders in which you can go through the cities. It's an enormous space, and the way algorithms that, in your GPS and things like this search for a path is that they search through among all possible paths for one that is the shortest. All reasoning systems are based on this idea of a search. Okay, in a space of possible solution, you search for one that matches what the objective that you want. So the way current systems are doing this, current LLMs, is in a very, very primitive way. They're doing this in what's called token space, which is a space of outputs. So they basically have the system generate lots of different sequences of tokens, more or less randomly. And then they have another neural net looking through all of those hypothesized sequences for one that looks the best. And then it outputs that. It's extremely expensive because it requires generating lots and lots of outputs and then selecting good ones. And it's not the way we think. So we don't think by generating lots and lots and lots of actions and then looking at the result and then figuring out which one is best. That's not the way we think. If I ask you, for example, imagine a cube floating in the air just in front of you, okay? Now take that cube and rotate it by 90 degrees around a vertical axis, okay? So you have a cube, rotated by 90 degrees. Now picture that cube and tell me if it looks like the original cube before you rotate it, okay? And the answer is yes, because you know that a cube has, is, if you rotate it by 90 degrees, it's still a cube, and you're still seeing it from the same viewpoint.
You mean that is illusion of free reasoning?
Well, so what you're doing is that you're reasoning in your mental state. You're not reasoning in your output action space.
In the physical world.
In the physical world. Or in whatever your output state is, right? You're reasoning in an abstract space. And so we have those mental models of the world that allow us to kind of predict what's going to happen in the world, manipulate reality, predict in advance what the consequences of our actions are going to be. And if we can predict what the consequences of our actions are going to be, like rotating a cube at 90 degrees or whatever it is, then we can plan a sequence of actions so as to arrive at a particular goal, right? So, whenever we accomplish a task consciously, all of our mind is focused on it. And we think about like, what sequence of action do I have to do to, assemble this piece of, IKEA furniture or whatever, or build this thing out of wood, or just, do anything. Basically, everything we do every day that we use our mind for are tasks of this type where we need to plan. And most of the time we plan hierarchically. So we don't, for example, you're going to go back to Warsaw at some point, right? If you decide right now to go back to Warsaw from New York, you know that you have to go to the airport and catch a plane. Okay, now you have a sub-goal going to the airport. And this is what hierarchical planning is about. You define sub-goals to an ultimate goal. Your ultimate goal is go to Warsaw. Your sub-goal is go to the airport. How do you go to the airport? Well, we're in New York, so you go down on the street and you hail a taxi to the airport. How do you go down on the street? Well, you have to move out of this building, go to the elevator, take the elevator down, move out. How do you go to the elevator? You have to stand up, go to the door, open the door, etc. And at some point, you get down to a goal that is sufficiently close that you don't need to plan, like to stand up, from your chair. You don't need to plan because you're so used to doing it, you can just do it, right? And you have all the information that's necessary for that. So this idea that we're going to need to do hierarchical planning, that intelligent systems need to do hierarchical planning, is crucial. We have no idea how to do this with machines today. That's a big challenge for the next few years.
That's why you spend so much time at Davos talking about the robotics. You spoke about a coming decade of robotics. Robotics had endless winters. Why is this time different?
Robots are usable in tasks that are relatively simple and can be kind of automated in a very simple way. So where the sensing doesn't need to be hard. So you have manufacturing robots that paint cars in factories and assemble parts and things like that. As long as everything is in the right place, and those robots basically are just automata. But then let's take another task for like driving. A self-driving car is a robot, or a car that has driving assistance is also a robot. And we still don't have self-driving cars that are as reliable as humans yet. I mean, we do, but there's Waymo and companies like that, but they cheat a little bit. They use sensors that are much more sophisticated than human sensing.
But Musk said that Tesla would reach 5-level autonomy within next 5 years.
He's been saying this for the last 8 years. He said, this is going to happen next year for the last 8 years, and obviously it hasn't. You clearly have to start believing him on this because he's been consistently wrong. Either because he thought he was right and he turned out to be wrong, or he was just lying. I think it's a way for him to kind of inspire his team to kind of reach unattainable
progress
goals, right?
Year after year.
Yeah, but I think it's actually very difficult for an engineer or a scientist to be told by their CEO, the problem you've been devoting your entire career to solve, we're going to solve it next year.
So you think that is the biggest challenge of our era, to integrate AI and robotics?
If we are able to build AI systems that understand the physical world, that have persistent memory, can reason and plan, then we'll have the basis for AI that can power robots that would be much more flexible than current robots that we have. So there's a lot of robotic companies that have been formed over the last year or two. They build humanoid robots and things like this. And all the demos are really impressive, but those robots are very stupid. They cannot do what a human can do. Not because they don't have the physical ability, it's because they just are not smart enough to deal with the real world. And so a lot of those companies are counting on the fact that AI is going to make fast progress over the next 3 to 5 years, so that when they are ready to sell those robots at a large scale and build them at a large scale, they'll be smart enough because AI would have made progress. It's a big bet. So I can't tell you whether it's going to happen within the next 3 or 5 years, but it's very likely that we're going to make significant progress in AI that is going to enable more flexible robots within the next decade, which is why I've said the next decade is the decade of robotics.
Are you surprised when you look at AI development today, the progress day after day, night after night?
Not really, no. No, what surprised me was the fact that it was very highly non-continuous. The fact that there was a lot of progress in the 1980s and 90s, and then nothing. And then some more progress during the 2000s, but it was under the radar. Most people didn't realize we were making progress. And then as soon as those progress became visible around 2013 or so, then the whole field exploded, and all of a sudden, a lot of smart people started working on it, a lot of companies started investing. There was a lot more interest. So now progress has been accelerating just because there was more investment and more smart people working on it. But I would have thought the progress since the 1980s would have been much more continuous. If a piece of research or development is published, so the techniques that are used to produce it are published in a paper or white paper report of some kind, and if the code is open source, then the entire world profits from it, okay? Not just whoever produced it. The person who produced it or the group that produced it gets prestige, okay, and recognition, and perhaps, investment or whatever, but the entire world profits from it. This is the magic of open research and open source software. Meta, I myself and Meta more generally have been extremely strong proponent of this idea of open research and open source. And whenever an entity that is practicing open research and open source produces something, the entire community of open source profits from it as well. So people are kind of formulating this as if it's a competition, but it's not. It's more like a cooperation. The question is, do we want this cooperation to be worldwide? And my answer to this is yes, because there are good ideas coming from everywhere in the world. Llama, for example, the first model, the first LLM that Meta put out. Yeah. It wasn't the first LLM. There were LLMs before that we put out, but they were a little bit under the radar. It was produced in Paris, in our labs in Paris. And so this is
Your
not,
lab.
which I created
Yeah.
10 years ago. Okay. This is Fair Paris. Has over 100 researchers there working. So, and a lot of really good stuff came out of that lab in Paris. A lot of good stuff came out from our lab in Montreal. So the research community is really worldwide. Everybody contributes. No entity has a monopoly on good ideas, which is why open collaboration makes the field progress faster. That's why we are big proponents of open research and open source, is because the entire field progresses faster when you communicate with other scientists. Now, there are some people in the industry who used to kind of practice open research and clammed up. That's the case for OpenAI. Anthropic was never open, so they keep everything secret. Google kind of went from being partially open to being open essentially because of us to now being partially closed. They're not revealing all the techniques behind Gemini, for example. They're still doing a lot of open research, but it's more kind of fundamental long term. I think it's sad because a lot of people are kind of basically putting themselves outside of the world research community and not participating, not contributing to progress. The reason why progress in AI has been so fast in the last 10 years is because of open research. And you have to realize that everybody...
You really believe it?
Oh, absolutely. No, this is a fact. I'm not the only one. It's not a belief, it's a fact. Let me give you an example. Almost practically the entire AI industry builds, or at least at the research and development stage, uses a software to build a system called PyTorch. PyTorch is open source. It was produced by my colleagues at Meta, at FAIR initially, and then a bigger population. A few years ago, the ownership of PyTorch was transferred to the Linux Foundation. So Meta does not own it anymore. It's still the main contributor, but it doesn't control it. It's controlled by a community of developers, essentially. The entire industry uses it. If that includes OpenAI, it includes Entropic. Google has their own thing, but it includes Microsoft, it includes NVIDIA, it includes everybody. Everybody uses PyTorch. The entire academic world research uses PyTorch. I think among all the papers that appear in the scientific literature, PyTorch is mentioned in something like 70% of them. So what that tells you is that progress in AI builds on each other's work, and that's how you make science and technology progress.
Maybe Stargate project would change everything.
No. Now all the companies that are involved in AI are seeing a future, pretty near future, where billions of people will want to use AI assistants on a daily basis. I'm wearing a pair of glasses now. I don't know if you can see it, but it's got cameras on it. These are the Ray-Ban Meta. Okay, they're built by Meta, and you can talk to them. There is an AI assistant that is connected to, and you can ask it any question. You can even ask it to kind of recognize a species of plant from the camera and everything. So we see a future where people would be kind of wearing smart glasses or maybe using their smartphone or other smart devices, and basically will use AI assistants all the time in their daily lives. They will help them in their daily lives. Now, that means there's going to be billions of users of those AI assistants using them multiple times a day. And for this, you need a very big infrastructure of compute, because running a LLM or an AI system, whatever it is not cheap. So you need a lot of compute power. Most of that investment, so Meta is investing this year on the order of 60 to 65 billion in infrastructure, mostly for AI. Microsoft has announced they're investing 80 billion. And then Stargate is 500 billion, but it's over 5 or 10 years, and we don't know where the money is coming from. So it's on the same order of magnitude of investment. It's really not that different from what Microsoft and Meta are already doing. And most of it is for inference. So it's for running AI assistant to serve billions of people. It's not for training large models. That is actually relatively cheap.
I have a question from our viewer. You propose an alternative to the transformer, which is the most important piece of LLMs. How does JIPA world model differ from transformers, and why do you think world models are the future?
Okay, so there is this architecture which really should be called a macro architecture called JEPA. So that means Joint Embedding Predictive Architecture. And it is not an alternative to transformers. You can have transformers inside of JEPAs. Okay, JEPA is kind of a macro architecture within which you arrange different modules, and those modules could be transformers. They could be other things if you want, but they could be transformers. So it's not; those are orthogonal concepts. It's not they're not in opposition if you want. What JEPA is an alternative to, it's an alternative to something that doesn't have a common name, but basically are the current crop of large language models. In the business, they're called autoregressive decoder-only architectures, or transformers, or OpenAI calls them GPTs, okay, general purpose transformer. So a GPT is just a particular, and by the way, it doesn't need to be a transformer, but it's a particular architecture that's trained using this self-supervised learning technique I was describing earlier, where you take a sequence of symbols, let's say text, a sequence of words, and you train a system. The system is organized in such a way that to predict a particular word on the input, it can only look at the ones that are to the left of it. Okay, it's called a causal architecture. And if you train a system you feed it a text and you just train it to reproduce that text on its input, then basically implicitly you train it to predict the next word in a text, all right? So then you can use that system, once it's trained, you can use that system to just produce one word after the other autoregressively, and that's what large language models are. Now, try to apply this to the real world, because you want to train a robot to, plan things or predict what's going to happen in the world. And it doesn't work. So if instead of words, you take frames from a video and you turn those frames into things like tokens, like the words, and you try to train a system to predict what's going to happen in the video, it doesn't work. It doesn't work very well. And so we have to, and the reason it doesn't work is because there's a lot of things that happen in the world that you simply cannot predict. And representing the fact that you cannot exactly predict what's going to happen is essentially a mathematically intractable problem in high-dimensional space like videos. It's possible in discrete space like text. So you cannot predict what word comes after a text, but you can predict the probability distribution of all the possible words. We don't know how to do this with videos. We don't know how to represent a distribution over all possible video frames. And so, so the techniques that are used for text, that work really well for text and for DNA sequences and proteins, do not work for video or other natural signals. So JEPA is an answer to this. It's a way to basically, the main idea is that instead of making that prediction in the space of the inputs, you train the system to learn an abstract representation of the input and then train it to make prediction in that representation space. And that turns out to be a much better way of formulating the problem. Because, if I take a video of the room we are in right now, or any room, okay, and I point the camera at one location, and then I slowly turn the camera, and then I stop and I ask the system, tell me what happens next in the video. The system might predict that the camera is going to keep turning, but there's no way it can predict all the details of what's going to be in the field of view after the camera rotates. There is a plant, there might be a painting on the wall, there might be people sitting. It cannot predict what those people are going to look like. It cannot predict what the species of the plant is, or what the texture of the floor is going to be, or things like that. It's just impossible to predict. And so if you're training a system to make those predictions, it spends a huge amount of resources trying to predict things it cannot predict, and it fails.
The greatest achievement of Yann LeCun laboratory is?
There is no Yann LeCun laboratory. It's hard to put the finger on it. I mean, what I'm known for is something called convolutional neural network, which is a particular architecture inspired by the architecture of the visual cortex, designed to handle natural signals like images, video, audio, speech, things like this. And those systems are used everywhere. So if you have any kind of driving assistance system in your car, and all the cars sold in the EU now have to have that, right? At least they have to have a system that brakes your car automatically when there is an obstacle in front of it.
That's your laboratory.
It's using convolutional net, okay? All of them. That's my invention from 1988, okay? It goes back a long time. So that's what I'm most famous for. The first applications were character recognition, handwriting recognition, reading zip codes, reading checks, the amount of checks, things like that. That was in the early 90s. And then since 2010, roughly, there's been like a very quickly growing set of applications for this. When you talk to your phone, speech recognition systems, the first few layers of the neural net that does this usually uses convolutional nets. When you have an application on your phone that you can take a picture of a plant and ask your app what is the species of that plant or species of that insect, or listening to the song of a bird or something and tell me what species it is, that's a convolutional net.
Where is the place of Europe in that AI race?
I think Europe has a very important role to play because Europe has the most difficult thing to
implementing regulations.
Well, there are issues of that type in the EU, that's for sure. Like, for example, the glasses I'm wearing right now. One application of this is, interpreting the images that go through the camera. So you can look at a menu. I could look at a menu in Polish, or you could be speaking to me in Polish, and there would be kind of translation of the menu. Actually, that's available today. That's available today in those glasses, except
but the glasses are not available.
The glasses are available in Europe, except the vision feature.
Except the vision
is not available because of uncertainty about regulation. It's not even clear the regulation would make it illegal. It's just that it's unclear. But let me say that Europe has big assets, big advantages, and the first one is talent. So
our programmers, mathematicians, physicists,
computer scientists, engineers, more generally, physicists, etc. A lot of top scientists in AI, regardless of where they work in the world, come from Europe. I come from Europe.
I remember the Nobel Prize conference when I asked Geoffrey Hinton.
My first question is to Professor Geoffrey Hinton. Do you regret something?
And I would like to ask you the same question.
I don't know what Jeff answered to that question, but I can guess what he answered. Okay, let me give you my answer first. Okay, so my answer is, for the longest time, I was not interested in what we now call self-supervised learning because I thought it was badly formulated as a problem. And in fact, I had those discussions with Jeff Hinton for many years where, I was pushing supervised learning and he told me, like, ultimately we need to figure out how to do what he calls unsupervised learning, which is now a particular form of it called self-supervised learning. And I only changed my mind about this in the mid-2000s. Okay. And that was probably 10 years too late. So I should have probably gotten interested in that problem earlier. But the thing is, between the mid-90s and the early 2000s, not much happened in neural nets and deep learning because the whole world was completely uninterested in that. So, we had to do something else. I worked on something else. I worked on image compression, a system called DJVU, which I heard was pretty popular in Poland, actually. In Eastern Europe more generally, but so I think that's one thing I would have done differently. Other than that, I've been pretty happy with things, the way things have been going. I would have been a little more forceful also at kind of keeping the interest of the community in neural nets and machine learning in the late 90s than I was. So that there wouldn't have been a kind of a winter of deep learning, if you want, right? I'm guessing perhaps one thing that Jeff might have answered is that he had a bit of a change of mind 2 years ago, where the quest of his career was to figure out the learning algorithm of the cortex of the brain. He always thought that backpropagation, which is the main technique that we use to train neural nets today, which he had something to do with, and I had something to do with as well. He always thought that was not what the brain used because, and the brain must be using something else because backpropagation is not really kind of biologically plausible. And so he kept coming up with sort of new ways of doing machine learning every 2 years for the last 40 years. And 2 years ago, he just gave up. He said, well, maybe the brain doesn't use backpropagation, but backpropagation works really well, and maybe that's what we need. Maybe it works even better than whatever it is that the brain uses. And so he had this epiphany and then retired. Basically, he could declare victory.
Thank you very much for your time and having you here. It was
Thank
a
you so
great
much.
honor. Thank you.
A pleasure.